and 12a minus 15b equals negative 33. So now at this point, I can add the left sides and the right sides together. The reason I can do that is like, if I think of adding, like, if I think of starting with the one on top and adding negative 33 to both sides, like we all agree I can add negative 33 to both sides, right? Well, this is equal to negative 33. So if I add that on the left and I add negative 33 on the right, I'm adding the same thing to both sides because those two things are equal. So that's why we can like add equations, is because really we're just taking one of the equations and adding the same thing to both sides. So this gives me 22a, and then 15 plus negative 15 is 0, and 55 plus negative 33 is 22. And that achieved my goal here, right, to get rid of one of my variables. And then we're back right in that situation we were in yesterday where we now have an equation in a single variable that we can solve. So I have 22a equals 22. So a equals 1. And then to get b, I can substitute back into either of the equations. In fact, I can substitute back into either one of these or either one of those secondary equations. It's not super practical for me to use the secondary equations in this case, but like we'll see in the next problem, like if you've cleared fractions, it's much easier to substitute back into an equation that doesn't have fractions than into one that does. So any of the equations along the way you can use to solve for your second variable. I'll just use 2a plus 3b equals 11. So 2 times 1 plus 3b equals 11. That gives me 3b equals 9. So b equals 3. So my solution is 1, 3. So this is just a different method of doing the same thing we did yesterday. There's not like a right or a wrong method. There's not like, you don't have to like pick the right one for a certain type of problem. Both methods will always work to solve any system. It's just a matter of like sometimes one of them is a little bit more efficient or a little bit less messy than the other one. So it's good to kind of know both. Most people I know like prefer one over the other and use it most often, but it's nice to have like kind of both of them in your toolbox if you need them. Any questions on the general process we used here? Okay, so let's do this one. So when I look at that, I don't get super excited about all those fractions. And so just like we did when we were solving equations in one variable, the first thing I'm going to do is just clear fractions. Like I'm not going to worry about anything else except for getting rid of all the fractions. And then I'll deal with eliminating or substituting or whatever. So I'm going to multiply the first equation by 10 on both sides because that's the LCD of 5 and 2. So we've got 10 times 1/5 x plus 1/2 y equals 10 times 6. And then that second equation, my LCD is 6, and so I'll multiply both sides by 6. So we have 6 times 1/3 x minus 3/2 y equals 6 times negative 8. So simplifying, let's see, 10 times 1/5 is just 2. So I have 2x, 10 times 1/2 is 5, and 10 times 6 is 60. And then 6 times 1/3 is 2. Half of 6 is 3 times 3 is 9, so we have negative 9y. Oh, I know what I did wrong last time. In my 8 o'clock class, I could not figure out why it turned out differently than I thought it was going to turn out, and I just saw a negative sign that I wrote as a plus sign. So at this point, oh wait, no, it's a plus sign. I want to change the sign. Anyway, at this point, I think about maybe eliminating. Do you guys want to eliminate x or y? X. Yeah, I'd probably eliminate x also because I see 2x and 2x. And so if I multiply one of those equations by -1, then I'll have 2x and -2x. So I'm going to just multiply the second one by -1. And so my new system, my first equation stays the same. And I have -2x. See, that is a plus sign. This one turns out really kind of nasty, but luckily we have calculators. And so now that I have my opposite coefficients, I can add. And we get 0 plus 14y equals 108. And I always write that 0 there because if it so happened that I was in a situation like where there was no solution or infinite number of solutions, then like both of those would 0 out. And if you do the thing where you just like cross it out like this, then you end up with just nothing on that side of the equation. So it's nice to actually like write a 0, even though you'll just drop it in the next step, because if all you have left on that side is 0, like you need something there. But now we can drop it. So 14y equals 108. So y equals 108 over 14, which simplifies to 54 over 7. I told you it doesn't work out very nicely. But what's cool is that it's not messy up until the very end, right? We were able to get rid of those fractions and set this up so that it didn't get yucky until like basically the final answer. So I didn't have to deal with fractions all the way through, even though it was kind of a nasty fraction as my final answer. So now I have to plug that back into one of my equations to solve for x. Again, like I have no desire whatsoever to plug 54/7 into either one of those equations. That seems pretty messy. But you can use any of the preliminary or the secondary equations that you get after multiplying. So I'm just going to pick 2x plus 5y equals 60. So we have 2x plus 5 times 54 over 7 equals 60. And if you still haven't figured out how to do fraction calculations on your calculator, you really should, because some of these can get really yucky. And I don't want you guys to get hung up on little things like that, because it can be discouraging when you totally understand the concepts and then like you get stuck on like some like a calculation that's just like doesn't have to do with the process, right? So let's see. I don't have my calculator. 5 times 50 for 250. 270. Oh, somebody might want to get their calculator out and make sure I'm not screwing this up. Equals 60. And then I have to subtract 270 over 7 from both sides. So 60 is 427ths. So subtracting gives me 157ths. And then dividing by 2 on both sides. Well, if that denominator wasn't there, 150 divided by 2 would just be 75, right? So this ends up being 75 over 7. And so my solution is 75/7, 54/7. Which is kind of yucky, but you know, sometimes it's good to see some of these messy things. Like, I feel like math books have these problems set up so that everything works out beautifully, and then when the numbers don't come out to be super nice, we get like kind of freaked out about it. But in the real world, like the numbers are probably not going to turn out to be super nice. Like nobody spent a bunch of time like manipulating the problems so that they would work out nicely, right? So it's okay to get messy numbers. It's okay to get nasty fractions. Like I said, use your calculator so you're not getting hung up on those calculations, but sometimes it just happens. But it won't here because I set it up, so it'll work out nicely. Okay, so now we're going to talk about solving applications using systems of equations. So a couple weeks ago, we solved application problems that had two unknowns, like a length and a width. But the relationship between the two unknowns was clear enough that we could do the whole thing in one variable, right? Like they told us like the length is 5 more than the width. So instead of calling the length y, we could just call the length x plus 5. So where we use systems is when those relationships aren't quite as obvious. So when the problem doesn't specifically tell us like how to find one if we know the other, it's harder to just write an expression to represent one. And so that's when we use two separate variables to represent our unknowns. Some problems you totally have a choice, like you can use a system of equations or you can use a single equation. The key is that the number of variables you use has to be the same as the number of equations you use. So if you decide to assign an x and a y, then you're going to have to come up with two equations in order to solve the problem. If you only use x, then you can write one equation. So we're going to do all these using systems, because it's good to practice. And these ones are the type of problems I would use systems for, because like it doesn't really tell us like how to find the number of 2-point shots if we knew the number of 3-point shots. I mean, we could do some manipulation to figure it out, but it's not like just right there in the statement of the problem. So it's a little easier to just assign each one of them a variable. So I'm going to say my unknowns are the number of 2-point shots. Use the word of. And the number of 3-point shots. And I'm going to call one of them x and the other one y. And then most of these, like, they don't seem the same because they're all different situations, but most of these problems are essentially the same type of problem where you end up with two equations. One is like a quantity equation and has to do with the total number of things. And then the other one is a value equation that has to do with the total value of those same things. And value can be a lot of different things. Like it could be money. In this sense, it's points. Like so. One of our equations is going to talk about how many points we have, and the other equation is going to talk about how many shots we have. So our quantity equation is just focused on the total number of shots that are made. So that's x plus y. What should that be equal to? 27. And I know it's 27 because that's the number of shots, right? So that's where that quantity versus value comes in. This is points. So that's how much my shots are worth, whereas this is shots, that's how many shots I actually made. So that's my quantity. And then for your value equation, you usually have to multiply your quantity by something. So if you multiply the number of shots by the value of each shot, that gives you the total value of those shots. So my 2-point shots are worth 2x points. So 2 points per shot times x shots. And my 3-point shots are worth a total of 3 y points, so 3 points per shot times y shots. And what should that be equal to? 60. Good. So everything in the value equation is in terms of points. Everything in the quantity equation is in terms of shots. And so now I can solve this system. I'm going to use substitution because that first equation, it seems pretty easy to solve for y or x. So y equals 27 minus x. And then we'll plug that into the second equation. So we have 2x plus 3 times 27 minus x equals 60. Distribute. And that gives me negative x plus 81 equals 60. What is that, 21? So negative x equals negative 21. And so positive x equals positive 21. And then plugging back into my first equation, we have y equals 27 minus 21, which is just 6. And then just like any other application problem, we want to answer with a sentence, right? Ordered pairs don't really make much sense in terms of like shots and points. So we don't want an ordered pair because this situation doesn't really have to do with a graph, right? We just want to write a sentence. So they made, let's see, X was the number of 2-point shots, so 21 2-point shots. And 6 3-point shots. Any questions on our general process? Does it make sense how we're using those same 4 steps, just a little bit differently? Yeah? No? Maybe a little. Okay, let's try another one. So we have the difference of two numbers is 3. 2 times the smaller number plus 3 times the larger number is 39. Find the numbers. What are my two numbers? What do you want to call them? So we'll call them X and Y. How should I describe them in words? What now? So one way, if you're struggling with how to like say it in words, what do they call the numbers? Yeah, the smaller and the larger number. So that's what I'm going to go with, just because it's right there in the problem, and that way when I'm translating, I can use the same thing that I wrote. So smaller number. Oops. And larger number. And you could call them like the first number and the second number. However, in this problem, like it's really important to differentiate between which one's bigger and which one's smaller. So if you know that, like if you know that when you write first and second, like you mean that the second one's bigger, then writing first and second number is totally fine. Just make sure that you know which one's bigger. So if it says the difference of the two numbers is 3, how would I write that as an equation? What's difference mean? So what should my equation look like?
Y minus X equals 3.
Can you tell us why you didn't do X minus Y?
Because X is a smaller number.
Yeah, very good. So this is sort of the trickiest part of these problems, is that if you take a smaller number and you subtract a bigger number from it, you will get a negative. So if our difference is positive, then we have to write it as the bigger number minus the smaller number. You can, like, you'll get a system that you can solve the other way, but the numbers won't be right, because if you did X minus Y here, you would be saying that X was the bigger number and Y was the smaller number. But then when you translate that sentence, you'll probably use X as the smaller number and Y as the bigger one, because that's what you said. So you're not actually using the same number for the bigger and smaller in the two equations, and so you'll end up with something kind of funky. So just be really careful whenever there's a difference, and if the difference is positive, you set it up so you're doing big minus small, so that makes sense. And then we'll just translate this other sentence just kind of straight across. So 2 times the smaller number, which is X, plus 3 times the larger number, which is Y, equals 39. And so now we can solve. I'm going to add x to both sides to get y equals x plus 3. And then substitute that into my other equation. So we have 2x plus 3 times x plus 3 equals 39. 3x plus 9. And that gives me 5x equals 30. So x equals 6. And then y is 6 plus 3, which is 9. So on these problems, because the most common error is to switch up the subtraction in the beginning, it's always a good idea to double check that x is in fact smaller than y when you get your final answer. If you switch them, then you'd get a bigger number for x and a smaller number for y, but it wouldn't be like just these numbers swapped. Because of the way you translated the second equation, you would get completely different numbers. So it's not like we're just being picky about which one we're calling bigger and smaller. It's that if you treat one like the bigger number in one equation and the other one like the bigger number in the other equation, you're not going to get the right numbers.
Like 3 for x and 2 for y.
Right, like if you did x minus y here, you would be saying x is the bigger number. Mm-hmm. So if you then translate it as 2x plus 3y, you would be saying 2 times the bigger number plus 3 times the smaller number. Because if you write if you wrote x minus y, this would be bigger. So then if you wrote this same equation, you'd be saying 2 times bigger plus 3 times smaller, which isn't what our equation says, right?
Yeah.
So it's like a consistency thing. And it's really easy to get mixed up. So at the very end, just check that like x is in fact smaller than y. And that's usually a good indication that you translated it all correctly. So then we'll write a little sentence. The numbers are 6 and 9. Okay, I'm going to have you guys try the next one. And I would say that this problem is exactly like the points problem, like the basketball problem. The only difference here is that we're measuring value in money instead of points, right? But we have a certain number, like a total number of something that has a total value, and we know what each one of those things is worth on their own. Just like with the basketball problem, we had a total number of shots, total number of points, and we knew how many points for each one. So even though they appear to be different numbers or different problems because they're like different situations, really the setup is exactly the same. And we'll see kind of the same setup for a lot of different situations. So give it a try and see if you can figure it out.
Number of salads and sandwiches.
Mm-hmm.
X for the salad and y for the sandwiches.
Good.
So it would be 7.50 for the salad. The salad costs 7.50.
Mm-hmm.
And then the sandwich costs 9.50.
Mm-hmm.
And then you equal that to 181.5. I mean 50. 181.
So what do you have on your left? So you have a 181.50 here. What's on the other side?
Your salad, your cost of salad and sandwiches.
Which is what?
7.50 and 9.50.
Mm-hmm. So is it just 750 plus 950?
No, X and then
Okay, good. So you have to be a little careful with these. I often see things like this, which I mean, if x was equal to 7.5, then we wouldn't need to do the problem, right? If we knew what x and y were equal to, then we'd be done. And what that is saying is that we bought 7.5 salads, right? So we think we're just labeling, but what we're really saying is something completely different than what we mean. So we have to be really careful, because the whole idea of the difference between value and quantity is like probably the most important part of these problems, right? We have to separate out like or distinguish what things are worth from how many of them we have, right? So what we just wrote is our value equation. That has to do with what things are worth, right? So if I buy X salads, it is worth $7.50 times X. And my total value is $181.50. And then I also need a quantity equation for the total number of items I purchased. So I'm going to take the number of salads plus the number of sandwiches and get what, Adam? Say hi for me and then put it away. Thanks. 21. And so now we have a system we can solve. So think for most of these problems that we set up, you want to think kind of like we did with the basketball problem, and I sometimes just label them so I can keep them separate. Like, be like, okay, one of these has to do with money, and one of them has to do with lunch items, and I can't like mix the two, right? So I can't take the number of salads and the number of sandwiches and make it equal to dollars somehow. So I'm keeping things that have to do with money separate from things that have to do with just counting objects, right? Which is what we're doing with the quantity. So now we can substitute, let's see, y equals 21 minus x. And so 7.5x plus 9.5 times 21 minus x. Okay, you guys are going to have to help me out here. You're going to be up here all day trying to do these decimals.
199.5.
Thank you. Minus 9.5x equals 181.50. So we're going to get negative 2x on the left. And don't get too freaked out about the fact that we're seeing negative numbers at this point. Sometimes it's easy to like get to this point where we have negatives and be like, I can't have a negative number of salads, and like kind of freak out. But just follow it through and make, like, if your final answer is negative, then you can freak out. But in this case, like the negative numbers kind of like cancel each other out. So we don't want to get too worked up about it until we see what happens. Negative, like, 18, thank you. Whoops, I said it was negative. Equals 9. And then we can go back up to this equation, y equals 21 minus 9, so y equals 12. So we purchased 9 salads and 12 sandwiches. Any questions? Okay, last problem. This one really we're just looking at to see kind of how simple it can be when we're working with functions. Remember we saw yesterday that if we have two equations in function notation, you just have to set them equal to each other. So that's true with applications also. So this is sort of your classic example of a real life problem you could solve using systems. If you have a demand, so the models usually look like this, like supply increases as price increases because we want to sell more if we're making more money off of things, right? So on the seller side, they're willing to sell more if the price is higher. On the consumer side, as the price goes up, we will buy less, right? So as the price goes down, we'll buy more. And so it ends up looking something like this. We're doing it linearly, so, I mean, in real life, they're not really straight lines, but our model looks like straight lines rather than curves. But that's what, like, your sort of typical supply-demand curve looks like, and every businessman in the world is looking for the sweet spot where they won't have any excess goods, right? So the amount they make is the amount they can sell, and that way they're not losing money by tossing things out, right? And we call that the equilibrium point, the point at which, so like the price at which the amount that we supply is exactly the same as the amount that the consumer wants to buy. And so to find that point, we just solve the system of equations given by our supply and demand curves. And so because they're both in function notation, we can just set them equal to each other, just like we did yesterday. So we have 0.2q plus 695 equals negative 0.25q plus 9. So 0.45q plus 695 equals 9. 205, and this like does not work out very nicely. It's like 2.6, is that right? Or something 0.6.
Yeah,
4.6-ish. So I just rounded. If I was selling like mugs or something, I would round this to 5, but you can sell partial pounds of bacon, so it makes sense to have a decimal here. So that's the quantity that corresponds to my equilibrium point. To get the price, you can plug that back into either one of your functions. If you got the correct Q, you should get the same answer regardless of which function you use, although we rounded here, so they might be off by like a couple tenths or hundredths. P of Q, P of 4.6 equals 0.2 times 4.6 plus 695, which is like 7 something, 87, thank you. So we usually say something like equilibrium is reached I can't spell. No, I think it is an I. I want to say equal with an A, but it doesn't look right. Like that doesn't look right, but we're like it should be. Okay, it doesn't matter. Nobody really cares. Is reached at a price of $7.87 per pound, and quantity of 4.6, and this is measured in like million pounds. It's kind of an awkward sentence, but as long as you have all that information in there, it doesn't have to be a perfect. That is not an A. It's definitely not an A.
Equilibrium.
That doesn't look right. Nothing looks right. We'll have to Google it. Okay. Questions on that one? So it's kind of nice when they give you the equations, right? Because you don't have to do quite as much work.